welcome back to yet another video on our channel Euclid Mathematics. We have started lecture series on CSIR, NET, SET, GATE and other competitive exam. So from few days I'm explaining here some of the previous year question from CSIR, NET, SET, GATE. Okay, and within that I started a question from the complex analysis, linear algebra and other subject too. Now in my today's video I'm going to explain to you all one of the question which is from CSIR, NET for multiple answer question, which is from paper 3rd. Okay, so let's get start our today's example. I will explain to you all first of all example and then we go for the solution. So here in our question we have given which of the following is a true. Okay, so we have given 4 statement and we have to figure it out which one of the statement is a true. Okay, so our first statement, it says that tan z is an entire function. Okay, so let me explain what is mean by entire function first. Okay, so tan z is an entire function means it do not have singularity. Okay, the function which do not have singularity, like a pole, like a removable singularity, like a non-isolated essential singularity or isolated essential singularity. If our tan z do not possesses these types of a singularity, then we say that function is entire in a whole complex plane. Here what we do, we just go for expansion of a tan z and just find out whether any other singularity exists there or not. Okay, so tan z can be written as sin z upon cos z. Okay, and if I substitute cos z 0, why we substituting cos z 0? Because when we put denominator 0, we always get the pole. So put the denominator 0, that means put cos z 0 and check out whether it is having pole or not. Okay, so if cos z 0, then our function gives us a pole. Okay, denominator 0, then function gives us a pole. And what value for cos z comes 0? We know that cos 0, it is all odd values of a 2n plus 1 pi by 2. Okay, so that means all 2n plus 1 pi by 2 cos is going to 0. Okay, that means in our domain I found some point over here. This point gives the value for cos is a 0. So if a cos is 0, then our function gives us a pole. When we have cos 0, function gives us a pole, and if function gives us a pole, then we cannot say function is entire, because if entire they do not have pole or removable singularity or other non-isolated essential singularity. But I got the pole over here, so first option is wrong. Tan z is never an entire function because we got the singularity always exists there. Now in option number B, we have option B here. Tan z is a meromorphic function. So what is meant by meromorphic function? Meromorphic function means that function which has a finite singularity always pole. Okay, the function which finite singularity always pole and infinite singularity always essential singularity. Okay, so here we can see I got the pole here for 2n plus 1 pi by 2. Okay, so all the finite for finite value I got the pole here for our tan z. So for what about for infinite value? So for infinite value we convert z as a 1 by z. Okay, so here we can see our cos z gives a pole for finite value, but if we take f of z as a cos z for showing our function whether it is having essential singularity or not, if I consider f of z is a cos z, then f of z it comes f of 1 by z, it comes cos of 1 by 0. I have considered f of z instead of f of z. When we substitute limit as a z tends to 0 f of z, so cos z gives us a finite value. Okay, so that means finite for finite value our cos z which is having pole, but at infinite value like a limit as a z tends to infinity, okay, to our f of z here. So cos z gives at infinite value essential singularity. So that is limit as a z tends to 0 infinity f of z cos in z. Okay, so when we apply limit z tends to 0, it goes to the other condition like a limit as a z tends to 0 1 upon z. Okay, which is equal to 1 upon cos 1 by z. Okay, for for essential singularity, what we do, limit z tends to infinity, we check for infinite value. Okay, so for infinite value we check essential singularity exists there or not. Okay, so for that apply limit n tends to infinity to our f of z and prove it. Our function gives us a essential singularity. That means at the infinity value, at the infinite point, our function do not exist. It cannot give finite value or exist there. Okay, so limit z tends to infinity f of z. Okay, that means f of z I consider here cos z. Okay, which is a limit as a z tends to infinity over here. Okay, for this. So if I wanted to put the limit, so for infinity do not exist, or we may write as a limit as a n tends to z tends to 0 f of 1 upon z. Okay, instead of z I taken 1 by z, and limit n z tends to infinity I interchange as a z tends to 0. So both will have same meaning. Okay, both of the gives us the same meaning. So limit z tends to infinity f of z cos z into limit z tends to infinity here. Okay, I written in other language as a limit z tends to infinity 0 1 upon z, and limit z tends to 0 cos z converted into cos 1 upon z. Okay, so when I apply limit z tends to 0 here, so our function cannot give finite value or do not exist at all. Okay, so our function always gives us a essential singularity at the point of infinity. So cos z is having pole at a finite part of a complex plane. So that finite part over here, z is equal to n plus 1 pi by 2. So our first condition hold for meromorphic function. And second condition, it says that infinite essential singularity. So I also got the infinite essential singularity here, cos 1 upon z. It is not defining at a z tends to 0. That means limit z tends to infinity cos z not defined over here. Okay, so then we write essential singularity at infinity. Okay, our cos z is having here. Okay, our function, it is not defined at infinite essential singularity. Okay, it is gives us infinite essential singularity. So option number B, which is a tan z meromorphic function, it is always true here. Okay, so it is easier, we have to satisfy only these two conditions. Now here we have next, tan z has isolated essential singularity at infinity. Okay, so isolated essential singularity or non-isolated essential singularity. First of all, understand the definition for isolated and non-isolated. So non-isolated essential singularity, it says that if we have limit point of a pole, okay, at infinity, it gives us, our function gives us a limit point of a pole at infinity, then our function is a non-isolated essential singularity. So in order to prove our option number C, which is wrong, so we have to show our function tan z, which is having non-isolated essential singularity. That means it goes for C option, it goes to wrong. Okay, so for non-isolated essential singularity, what we do, we find always limit point of pole. Okay, so and we know that the pole for our function is a 2n plus 1 pi by 2 here. Okay, so which is a 2n plus 1 pi by 2, which is a pole of our function, which is the pole of a tan z. Okay, so we have to show our function gives us at infinity, gives us a limit point of a pole. Okay, so when we apply limit n tends to infinity, tan z always gives us a pole. So for all these values, tan z never defined. Okay, so these values are the pole for our tan z. Okay, so that means at infinity we got the limit point of a pole for our tan z, means this is the pole of a tan z, and at infinity it become limit point of pole. Okay, so at infinity it goes to the limit point of pole. So if it is a limit point of a pole, then we say that it is the definition of a non-isolated essential singularity. So our function tan z gives limit point of a pole, which is a non-isolated essential singularity. But in our option we have given tan z has isolated singularity at infinity. So our option number C is wrong. And the next option number D, tan z has a non-isolated essential singularity at infinity. So this is the converse part of option number C. If our option number C it goes to wrong, then option number D always true. Okay, so tan z is always having non-isolated essential singularity at infinity. Okay, that means at point infinity, so here tan z is having this amount of poles that cannot define tan z for this particular point. Okay, so that's why tan z is having non-isolated essential singularity at infinity. So I hope you all have understood my today's lecture. It is completely based on singularity chapter. Okay, so we have to define here only the singularity for tan z, and we included meromorphic function topic. So thank you everyone. Thank you for my today's lecture.